Okay, I want to do another example of finding extreme values, and I want to find all the absolute and local extreme values of this function here, 5x to the 2/3 minus x to the 5/3, on the interval from -1 to 3. Now, maybe not as obvious as the last example, but this is a continuous function. Um, the With it being cubed roots, it doesn't matter whether you got positive or negatives being plugged in there. So you can always take cubed roots, you can square them, you can raise them to the fifth, you can subtract. Nothing goes wrong here. This is a continuous function on the whole real line. In particular, it's continuous on the interval from -1 to 3. So with a continuous function on a closed finite length interval, there has to be an absolute max, there has to be an absolute min. Okay. In order to find those, there's one of three places where they might happen. They might happen at the critical points, derivative is 0 or the derivative is undefined, or they might happen at endpoints. So my two endpoints I already know, I'll use those to plug in, but let's find the critical points here. Let's find the critical values. So what I'm going to do is I'm going to take the derivative, because to find the critical values, either way, you're looking at the derivative, either equal to 0 or undefined. So the derivative is, what's this? 10/3 x to the -1/3 minus 5/3 x to the, if I subtract 1, that would be 2/3. All right, well, I'm going to factor this. I mean, there's several reasons why I factor it. One is because I know I'm going to set it equal to 0, so, but the other is um, I'm going to be able to see things a lot better, I think, if it's factored. So I can factor out a 5/3 x to the -1/3. And I choose the -1/3 because it's the smaller of those two exponents, right? So what's left here? There's a 2 left from the first term, and I got x to the 2/3, and I factored out, so I'm dividing out, which means I subtract exponents. So 2/3 minus -1/3 is 3/3, which is just x. All right, so I see a couple of things here. One is this negative exponent means that that's in the denominator. So this is 5/3 times. There's a 2 minus x in the numerator, and there's an x to the 1/3 in the denominator. That's actually going to create a place where the derivative doesn't exist. The numerator is going to create a place where the derivative is 0. So I have f prime of x equaling 0 if 2 minus x equals 0, which tells me that x equals 2. So that's one type of critical point. The other type of critical point is when f prime of x does not exist. Well, to get this to not exist, the only way we're going to do that is if, just looking at this, the only thing that could go wrong is I might be dividing by 0. Well, I'm dividing by 0 when this 1 over x cubed, sorry, 1 over the cubed root of x, whatever, the cubed root of x, this denominator, whenever that's equal to 0, then the whole denominator is 0, and the function is not defined here, or at least the derivative is not defined. So cubing both sides here, I get that x is equal to 0. So I've got two types of critical points here. I have the critical point where the derivative is 0 at x equals 2, and I have a critical point at x equals 0, critical point where the derivative is not defined at x equals 0. So on a button, where are we now? I have two critical points and two end points, right? There we go. So I want to look at what is f of -1, what is f of 0, what is f of 2, and what is f of the other endpoint. What's the other endpoint? 3. And I'm just going to plug those back into my original function if I can remember what my original function was. Ah, yes, the original function is this one, 5 to the 2/3 minus 5x to the 2/3 minus x to the 5/3. Okay, so I've got 5 times -1 to the 2/3 minus -1 to the 5/3, yes, which is equal to This is 5. So this is the 5/3. So this is 5 minus -1. So this is 6. Plug a 0 in. Well, that's going to be the easy one. 5 times 0 to the 2/3 minus -1. Sorry, minus 0 to the 5/3, which is 0. Plug a 2 in. I've got 5 times 2 to the 3, so the 2/3 minus 2 to the 5/3, which is equal to, this is equal to 5 times 3 to the 2/3 minus 3 to the 5/3, which equals 4.16 something, right? So did I never figure out the 2 here? Did I never figure out what 2 was? I didn't. Hang on a minute here. Let me go back and finish that. All right, it's 4.7622. It's interesting, the phone's been ringing off the hook here, so I keep interrupting this, and maybe you've noticed that it keeps breaking the video here. So what do we have here? I see a smallest value of 0, so I have an absolute min of 0 at x equals 0. I see an absolute max here of 4.7 of 4.7622 at x equals 2, and I see endpoint maxes or mins. Wait, 6 is bigger than 4.7, isn't it? So, well, goodness, I don't know how I overlooked that, but I'm sure you caught it before I did. So we have an absolute max of 6 at x equals -1. At x equals -1. So this right here must just be a local max of 4.7622 at x equals 2, and then I've got this endpoint, something going on at the endpoint there. Now, one of the things we'll do next week is do some graphing and see how the derivative is going to help us draw some graphs. But the graph of this thing looks like this. It's got an intercept here at 5 and 0, and that high point there was at 2, but the 6 was up here at -1, and this thing that's happening here at x equals 3 is just, we're looking from here to there and stopping. So this is kind of a local min, but it's sort of an endpoint min, right? So there you go. The general way that we find maxes and mins is we find where they might happen and then plug them into the function to see what's going on. In section 4.1, we're really only dealing with continuous functions, and we're dealing with intervals that are closed and of finite length. We move on a little bit. There's some things that you got to be able to deal with, and we'll see that. But let me just give you one example of this before we finish this video. I mean, if you look, for instance, at something like f of x equals, how about 1 over x plus x? Right? Now notice this has got a vertical asymptote at 0. So even if I look, if I look at an interval that doesn't have 0 in it, then there's no problem. The only discontinuity of this function is at x equals 0. But if I look at an interval that contains 0, so if I look from, like, say, -5 to 5, I can still do the, find critical values. F prime of x is, that's x to the -1, so minus x to the -2 plus x, right? which, let me write it this way, minus 1 over x squared plus, oh sorry, take the derivative. Again, keep me honest here, right? Derivative is plus 1 there. So getting a common denominator, this looks like an x squared minus 1 over x squared. Okay. This tells me a couple of things. This tells me that f prime of x equals 0 when the numerator is equal to 0. So that's x is plus or minus 1. And f prime of x does not exist when the denominator is equal to 0, which is at x equals 0, which probably isn't too surprising that the derivative doesn't exist at x equals 0 because the function doesn't even exist at x equals 0. Interestingly, in this one, with x is plus or minus 1 there for those critical values, if you look at the function value at 1, that would be 1 over 1 plus 1, which is 2. And look at the function value at negative 1, that would be 1 over negative 1 plus negative 1, which would be negative 2. You'd think, oh, look at this one is bigger than that one, so this one looks like it's a max and this one's a min. However, that's exactly wrong. The graph of this function looks like this. And at x equals 1, you actually have a local minimum value. And at x equals minus 1, you have a local maximum value. Okay, so just because this value is bigger than that one doesn't mean that this is a max or a min, right? In the event that you've got a continuous function, then it's a little easier to tell that you've got this sequence of lower values and higher values. But when it's discontinuous, then you can have what looks like a low value be actually locally high, and what looks like the high value be actually locally low. So just be careful that you know you're dealing with a continuous function. Or if you're not, then just be a little more careful. We will look at how to get these graphs and how to use this derivative next week. Derivative and the second derivative will tell us a lot about what the graphs look like. Anyway, there's extreme values for you.